Hi everybody. I'm Drew, and I'm a PhD student at McMaster University up in Canada. And my job is to detect and characterize exoplanets, especially planets around small stars, um, which, as you can expect, relates quite closely to this presentation here today about exoplanet detection methods. How do we find them? Just to get started, to get a little bit of an idea, I want to take a look at the distribution of the number of exoplanets that we found. Ever since we discovered the first exoplanet back in, 1992, we've been looking for planets up in the sky, and we've been finding them in exponential rates. As of today, we found over 6,000 planets. And at the rate we've been going, we've been finding about one a day for the last several years. And if you look right here, this plot shows the distribution of planets we've discovered over time, sorted by discovery method. Each color corresponds to a different method of discovering planets. And as you can see, two methods, the purple and the green here, corresponding to the transit method and the radial velocity method, are responsible for the vast majority of exoplanet detection. Now, because we only have like 15 minutes or so to go ahead and do this presentation, we are going to stick pretty closely to those two methods, talk about them in detail, and then maybe if we have time, briefly go through the other methods up here. So the first one we ought to talk about is the transit method. That's the one that's responsible for this purple right here, responsible for the vast majority of exoplanets that we've. And the way I like to, and so the transit method is essentially observing the dip in brightness of a star as a planet passes in front of it. So, like, imagine looking at a light really far away. It's so far away, like the stars in the sky, that you can't actually resolve the shape of the light. You can only see it as like a single point. Now imagine somebody standing next to the light decided to cover part of it up. You would suddenly see it get dimmer, right? And if you saw it suddenly get dimmer out of nowhere, you might say that something must be covering it up. And stars work the exact same way. If a planet orbiting a star happens to line up just right, it's going to what's called transit the star, which is a fancy way of saying pass in front of it. And if it does that, it's going to block some of the star's light, and we are going to see a sudden dip in how bright the star appears. So we can see it down here. Up here on this top left panel is like a top-down view of a planet orbiting around a star. And this plot here on the bottom left is what we would see from Earth's point of view. We see the blue planet going in big circles or ovals or whatever around the star. And then eventually it's going to transit the star, so pass in front of it right here. Now, we can't actually resolve the star, and typically we can't resolve the planet. So all we see is the star suddenly get dimmer. And we typically see the star as a single pixel in a telescope or in a camera or in a telescope right here on the bottom right, which means that as we see the planet pass in front of the star, we don't actually see the planet. We just see the star get a little bit dimmer, like we're about to see right now. And so typically, what astronomers will do is we will make plots of how bright these stars are over time. So we can see up here on the top right, the star is bright, bright, bright. And then as the planet passes in front of it, it's going to get a little bit dimmer. And then as the planet moves away, it's going to get brighter again. And so we can learn a lot about the planet that we're studying just from this. For starters, we can figure out how long a Uranus planet is, or the planet's orbital periods. The planet, like we saw, passes in front of the star exactly once every time it goes around the star. And so by measuring how long it takes between transits, we can figure out how long a Uranus planet is. But the big thing we can see is how big this planet is, the planet's radius. Because bigger planets will physically block more light from the star, because they're bigger. And so it's going to, and so we're going to see a larger dip in the brightness of the star when that happens. So if we want to quantify that, we can quantify it with this equation up here. By calculating Z, the transit depth, i.e. the fraction of the star's light that's blocked. For example, with this over here, we see the star suddenly go to 94% of its original brightness. And so it got 6% dimmer. So Z would be 0.06. And we can calculate the radius of the planet with this equation right here. Z is equal to the radius of the planet divided by the radius of the star squared. Now, typically, we can just see Z. We can see how much the star dims. We can see our star, the radius of the star. That's something we typically know. And so from there, we can infer the radius of the planet. Now, this transit depth is usually really small. Even for a planet like Jupiter around the sun, that transit depth is going to be a 1% dip in brightness. And for something like the Earth, that dip is going to be more like 0.01%. But it's something we can measure with our telescopes. And from there, we can infer the radius of the planet. The one downside is that these planets need to be perfectly aligned to pass in front of their star. Oh, yeah, sorry, question from Yavresh. What does the percentage mean here? 1% what? That is how much dimmer the star is going to get. How much of the star's light is being blocked by the planet. So if Jupiter were to pass in front of the star, in front of the sun, it would get 1% dimmer from the point of view of, an alien looking at the Earth. We would see 99% as much light. Now, the downside is that these planets do need to be perfectly aligned to pass in front of the star. And we can quantify that with something called the inclination of a planet's orbit. That's essentially the angle that the planet's orbit is at compared to our point of view, compared to the Earth. An inclination of 0 means that the planet is orbiting like perfectly around the star, like this, in a big circle. So like the planet's orbit is face on. An inclination of 90 degrees means that the planet's orbit is edge on, we call it, meaning that the planet is going to pass in front of the star from our point of view. And it can take the inclination can take any value. But we can only see the planet if it actually transits in front of the star, meaning if its inclination is 90 degrees or very, very close to it. And for the record, most planets are not going to have an inclination like that. The odds of a planet having just the right inclination for us to see is roughly equal to the radius of the star divided by the semi-major axis, meaning how far away the planet is from the star. And that number is very low. For example, for the Earth, the odds of the Earth transiting from the point of view of some other star is only about 1 in 200, about 0.5%. So we're only seeing a small fraction of the planets that are out there with us. Importantly, though, we are biased towards finding planets with a shorter period that are closer to their stars. It does mean that they're more likely to transit. But we're still not seeing most planets. The good news is this: we can just have planets looking at the entire sky and surveying large chunks of the stars that we can see in the night sky at once. And so even if only 1 in 100 or 1 in 200 planets are transiting, we're still seeing a whole lot of planets. And so all these purple dots here correspond to all of the planets that we've been able to discover with the transit method, or at least all the ones that have masses that we know of. And so we can see we are able to measure a whole bunch of planets with short periods, and especially bigger planets, because they're going to produce bigger signals. But of course, there are planets further out that we might struggle to see. And for those, we need to use something called the radial velocity. But it's a little bit complex. Sorry, Anushka asked, so the planets that are being discovered, are they in the fully face-on system? No, the exact opposite. These planets need to be fully edge-on, meaning that we're seeing just like the edge of the plane the planet's orbiting. If they're face-on, we aren't going to see them transit. They're not going to pass in front of the star. But to find those other planets, we can use another method called the radial velocity. And to do this, we need to take a step back and talk a little bit about physics. Talk about something called the Doppler effect. Have any of you guys heard of the Doppler effect? Yes? No? Okay, seeing a bunch of yeses, which is good, because it means I don't really need to talk too much about the Doppler effect here. Saves us some time. So, the radial velocity method is a method of finding planets where we see the planet's gravitational tug on its host star by way of the Doppler effect. So if you have a planet orbiting around a star, the star or the planet is going to go in big wobbles, big circles around the star. That's just how planets orbit. But of course, the planet still pulls on its star with its gravity, and that's something that actually affects the star. The planet's going in a big circle around the star, but the star is being pulled back and forth moving at a scale of like meters per second. But that's something we can actually measure. Just as the Doppler effect makes sounds from sources that are moving towards or away from you sound lower pitched or higher pitched, the Doppler effect makes light that's coming from a source that's moving towards or away from you a little bit redder or a little bit bluer. If something is moving away from you while emitting light, it's going to look a teeny tiny bit redder. And if it's moving towards you, it's going to look a tiny bit bluer. And this is something we can actually record. We can see a planet or star moving back and forth at a scale of meters per second with our best spectrographs being able to record tiny movements to the star's velocity towards or away from you, that small. And so this is what we see here. We have a top-down view of the planet's orbit, and of course a view from our point, or from Earth. And we can see the star's spectrum get a little bit redder or a little bit bluer as it moves to and away from the star. And we can keep track of what speeds towards and away from us that corresponds to. And we'll see the star undergo these sinusoidal signals, or sinusoidal-ish signals, moving towards or away from us. And we can infer that that's because of the presence of a planet. And of course, this is, just like transits, something that we can quantify. This here is a plot of the velocity of a star over time. Over the course of several days, from the star 51 Pegasi b. And so 51 Pegasi b is actually the very first planet that we discovered with this transit method. And we were able to learn a lot about this planet just from this method here. For starters, we see this big sinusoidal wobble only happen once every time the planet goes around the star. So by seeing how long it takes for the planet to go from do like one whole, how long the stars take to do one whole back and forth is the orbital period of the planet. We also know that bigger planets are going to produce bigger wobbles because they pull on their stars they have a stronger gravitational pull on their stars. And that's something we can quantify. The semi-major axis, the RV semi-amplitude, meaning the height of this sinusoidal signal, or half of the height, is equal to this, can be equal to this equation here. And so larger planets, larger MP, larger masses of planets, are going to produce larger signals, larger shifts in velocity from the star. Also, smaller stars are going to produce larger signals in the same way. And shorter period planets, planets that go around their star faster, are going to produce larger signals too. So this means that we can produce larger, or this means that we can produce, or we are doing a better job at seeing larger planets around smaller stars with shorter periods. And so if this planet is larger, it's going to pull in a star more. It's going to make it go back and forth stronger. And if the planet has a shorter period, we are going to go ahead and produce a larger signal too. Now, our best spectrographs in the world can find planets that produce radial velocity shifts, or RV shifts, of about 1 meter per second, or a little bit smaller. And that's really good. It's not good enough to find planets like our Earth, but it is good enough to find those sorts of planets around much smaller stars. For reference, the Earth around our sun will produce a radial velocity shift of about 10 centimeters per second. Now that's not great. We can't detect that. But if something like the Earth were closer to the sun or around a smaller star, then we would be able to see it. Now the downside is that unlike the transit method, we cannot survey the entire sky all at once. Typically, our best telescopes can only measure the radial velocity of one star at a time, and so it's a lot less efficient than transits. But the good news is, these planets don't need to be edge on. Remember, if we look at this right here, if the transit method only works if you have a planet that's perfectly edge on. But of course, what we're seeing here is that if a planet is just misaligned, if a planet's inclination is just small enough that it won't transit, then that's no issue. all it means is that the RV semi-amplitude is going to be decreased by a factor of sine I, which isn't that bad. It still means that we can see not every planet, but the vast majority of planets are still going to have measurable radial velocity signals. But at the downside of not being able to see all these planets at once. And so, like I said, the radial velocity method only works for planets, or we can see planets with a radial velocity signal of about 1 meter per second or lower. And this line, red line right here, very roughly corresponds to an RV semi-amplitude of about 1 meter per second. As you can see, all these planets with green squares are the ones that we can discover with this method. So we can see planets like Jupiter, see planets like Saturn. But of course, if we want to see planets as small as the Earth or Venus, they're going to need to be a lot closer to us. That said, the best planets that are the best spectrographs that we're building right now should be like an order of magnitude better, meaning that we can see planets somewhere around here, which of course means we're right on the edge of being able to see like the Earth. Now we are at 16 minutes already. So I'm just going to add a few closing notes, and we probably won't get to talk about the other discovery method. But I do just want to note that these two methods are not mutually exclusive. Most of the time, or a lot of the time, you will not see somebody only use the transits or RVs. Typically, you will see both of them at the same time. Because, of course, they tell you different things. Transits tell you about the radius of a planet. Radial velocities tell you about the mass. Those are two different things. Because combined, if you have the mass and you have the radius, you can figure out the planet's density. Meaning, you can figure out what these planets are made of. Planets that are made out of different things are going to have different densities. And so by having RVs and transits combined, you can learn a lot about what these planets are. Now, unfortunately, we are low on time, so I'm not going to be able to talk too much about the other methods. So before we talk a little bit about the homework, does anybody have any questions? Okay, doesn't look like there are any questions. Feel free to ask them at a later point if you have any. But just a brief note about your homework before I go ahead and turn it over. No, somebody asked if I could go back to the Doppler effect slide once. Yes, I can. This slide? The previous one? This one? All right, here we go. Yeah, just a brief note about your homework. So the homework that I've written is about analyzing some simulated transit and radial velocity data. So you can go ahead and see here, it's all in this Jupyter notebook that should be shared with you. In it, you guys are given some simulated transit data. You can see those dips that correspond to the transit. And some simulated radial velocity data. You can see that sort of sinusoidal-like signal that we know is because of a planet. In this, you are going to be going ahead and trying to fit this data by hand to try to find the mass and the radius of a planet from this data. And it's all contained in this notebook. There should be functions to do this for you that you just need to run and fit parameters. But it is there if you guys want to go ahead and try to fit this data by hand. Also, there is an optional section where you can have a computer fit the data for you. And then you can compare the results that you got with the results that the computer got to try to see where you went wrong or where you were able to do as well as the computer. So yeah, there we go. If anybody has any questions about it, feel free to ask them at any point. Yeah, it looks like we did get a question. What kind of data about a planet can you find with other discovery methods? Typically, it is basically the same things. It's just the mass, the radius, and the orbital period. There are also some other things you can measure, like the eccentricity of a planet's orbit, which you can also constrain with stuff like the radial velocity method. You can get into it here in the interest of time. But typically, those are the same things. So Emma asked, if we already have a transit method, why do we still need radial velocity measurements? Isn't the transit enough? So that's a great question. So the radial velocity method can absolutely characterize some things that the mass or that the transits cannot. For example, transits just tell you the radius, the size of a planet, but radial velocities tell you about the planet's mass, which of course is really important. It tells you about what this planet is made out of alongside the radius. It's important for being able to properly characterize the planet. Also, radial velocities can tell you some other data that transits might struggle with. For example, radial velocities can tell you about the eccentricity of a planet or of a planet's orbit, which I didn't get into here. But for the record, if a planet is on the centric orbit, you'll see the shape of its radial velocity signal deviate from this like perfectly sinusoidal measurement that you have here. And while that is something you can characterize from transits, you'll see the shape of the transit change a little bit. It's a lot easier to characterize it with the radial velocity method. Suffice to say, they measure different things, and they're both important. Other stuff, Uvraj. For beginners in Python, will some documentation be provided for the homework? Yes, it will be provided. Faye just mentioned, but the very next presentation is about Python. Uvraj also asked if we have a good sinusoidal signal. Does it mean a low eccentricity? And yes, it does. If the planet signal is perfectly sinusoidal, that does mean its eccentricity is very close to zero. You will have, meanwhile, if you have a very eccentric orbit, you can have a transit signal look or an RV signal look like this, or maybe something like this, or it can take on all sorts of weird shapes that depend on its longitude or on its eccentricity, and something called its longitude of periastron. It just means like how the planet's orbit is oriented relative to the Earth. So what if the exoplanet is at an unfavorable angle? Well, if it's at an unfavorable angle, you're not going to be able to observe it transiting. Its eccentricity needs to be basically 90 degrees in order for it to transit, give or take a fraction of a degree. But meanwhile, we can see here for radial velocities, the semi-amplitude of the signal depends on the sign of the inclination. So if a planet is at an inclination of like 45 degrees, for example, well, that just means the signal is smaller by a factor of like square root of 2, a factor of like 30%. That's still something we can characterize. So Anushka asked, can we determine the orbit of the system using the transit method? Yeah, we can tell, for example, what the period of the planet's orbit is based on how long it takes between transits of its star. We can also learn about its inclination because if it's transiting, its inclination has to be basically exactly 90 degrees. You can also learn about its epoch, aka the time of transit. That one's pretty simple. It's just when does the planet transit? There are other things you can learn too. You can learn about a planet's eccentricity, for example, where the transit will have a slightly different shape, but again, that's kind of outside of the scope of this. So Shub asked, if there's more than one planet orbiting, won't the signal look different for Doppler and transits? And the answer is yes. You will see multiple transits happen different times, typically with different depth, if there's multiple planets. And if you have the radial velocities, you will see two different sinusoidal or near sinusoidal signals superimposed on each other. So you'll see you have this signal right here, but say you also have a smaller signal that looks like this. Well, then if you try to plot your data, it's going to look something like this over time. And you look at that and say, hey, that looks like two sinusoidal signals superimposed on top of each other. That is probably two planets. Yeah. Other questions? What kind of planets should we aim to discover using the microlensing method? The microlensing method is something that we didn't get to talk about here in the interest of time. But suffice it to say, it does let us see medium distance planets, medium period planets. So planets that are like where Mars is or where Jupiter is, but not quite as far away as Uranus and Neptune. And again, what the microlensing method is, as well as why it does that, is well outside the scope of this presentation here. But suffice it to say, that's what happens. So Anushka asked, do we see any noise in the light curves, or is it solely the dip in the light curve by the planet? And the answer is, oh God, we absolutely do see a lot of noise for both transits and RVs. So one thing that I have completely neglected here is the presence of stellar activity. So stars typically have star spots. There are typically flares, stuff like that, that produce huge variations in both the brightness of the star and can produce signals that look an awful lot like the radial velocity signal. So the brightness of the star will change over time, typically in a different shape than transits, so something we can distinguish, but it does take work to properly model it out. And radial velocities, it turns out that if you have something like a star spot going around your star, well, one side of the star is moving towards you, and one side of the star is moving away from you. So if the star spot blocks or means less light coming from one side of the star than the other, it looks like a shift from blue shift to red shift. That looks like a quasi-periodic signal that looks an awful lot like planets. And so it's a big issue for trying to distinguish between planets and just stellar activity. Um, and how you do that is beyond the scope of this, but we can look at the data at the star with other data or other telescopes at the same time and see whether the signals look more like planets or like stars. I'm not going to get into it here. Your homework certainly does not. I did not add in any of that noise for the heck of it. But suffice it to say, this is a big problem. This is like perfect looking data. So, can these methods help identify if a planet has moons or other satellites? Yeah, absolutely. Typically, the transit method would probably be better at this, but the radial velocity method could be used too. Those would add on like additional signals from the planet, from the planet and its moon. But that's also something that's not part of the scope of this presentation here, so we're not going to get into it too much. So yeah, does anybody have any questions before we go ahead and move on to our next presentation?
Thank you so much, Drew. That was great. Folks, if you have more questions, feel free to post it our Discord channel or just email Drew directly. And the homework will be posted after the live session as usual. All right. Okay. Maybe we can move on to the next part, which is on Python, with which you can analyze the data provided by Drew. Okay, so the next session will be presented by Maria, but she could not be here today, but she sent me the recording. Let me show that. Just one sec.
So today I'm going to be talking about just giving you a very, very basic introduction to what Python is, what the notebook architecture is, which you would be utilizing throughout the duration of this course. My name is Maria Vincent. As I introduced myself earlier, I'm a graduate student at the Institute for Astronomy. So this generally falls. So for those who have checked out last year's tutorials on the course website and GitHub, it follows the general structure of the course of this tutorial, which was taught by Chetan last year. So yeah, here it goes. So what exactly is Python? To put it simply, it's an object-oriented programming language, which is quite easy and very beginner-friendly compared to a lot of other programming languages out there. Compared to C++, IDEO, Java, which is not very intuitive. Python is Python because of its quite simple syntax, because of how very closely it relates to just regular English sentences. Like if you want to display something, you would just say print so and so. If you want to add something, you would just do the number plus the other number, or the variable plus the other variable. So it is very easy to understand because of its simple syntax. It's beginner friendly, and and there are a lot of resources available. There's a lot of open source software modules and packages suited for various scientific and data purposes, which is why it's very popular. It can be used for data analysis, machine learning, to develop websites, to develop these automated scripts that just runs through rows and rows and rows of numbers. It can be used. Python's also used to create prototypes of softwares and to test it, and just for general everyday tasks, just to make some amount of processing and system operations a little easier. And fun fact is that it got its name from Monty Python's Flying Circus, just because the creator really liked the show and he wanted a name that was short, something mysterious that would immediately strike a chord with its users. So Anaconda, Miniconda from the many emails and messages on the course Piazza. So let's start from the basic. Conda is an open source package management system and environmental management system. What that means is it is basically this huge sack that contains a lot of different elements of creating and a lot of elements of creating and distributing software. It was primarily created for Python, but you can also use it for pretty much any language. Most people use it for Python and R. It comes in, it lets you sort of shift between different programming environments. And by that, what I mean is within your so you can think about it as like within a little city, you're creating these different buildings for different purposes. Within a city, you have a school for teaching, you have a hospital that takes care of the sick, you have a building for people to live in. In the same way, within Conda, you can create different environments that all have the same base way of operating, except that you might have some slight differences maybe between Python versions. Maybe you want one environment that has an older version of Python because some software can run only on an older version of Python. In another environment, you have a newer version of Python plus some extra modules because it operates differently. Then maybe you can have an environment just for astronomy because you have all the astronomy related packages. Now, what are packages, what are modules? You'll be slowly learning that over the course of the next few weeks. So I'm not going to dive into that real quick. But what you need to understand is just that Conda is very important because that's how you create your various environments. You manage your environments, and you can also install the various open source packages that you need to write or run a Python program. Anaconda is a single distribution system. It basically is, so you have Anaconda and Miniconda. I'll explain the difference between the two. Anaconda is a single distribution system. It already comes with a lot of scientific packages installed for basic scientific data analysis. So you don't have to install them separately. You still have to install a few that you need specifically for your field. For some astronomy modules, they don't come pre-packaged with Anaconda, so you have to install them separately, but most things do. And as I mentioned earlier, even in Anaconda, you can create these different environments to run Python differently or to add different packages to each. Miniconda is a much more minimalized, much more simple installer for Conda. So Anaconda comes pre-packaged with many things. Miniconda does not. It's just if Anaconda is a mansion, Miniconda is just a little cottage, basically. It doesn't come with all packages. You can certainly install them later. So I guess the pros and cons of Anaconda and Miniconda is mostly about storage. If you have enough storage and you don't want to install things separately, just go ahead, install Anaconda. But if you have very limited storage and you just need certain packages at different points of time and you're not sure which, Miniconda is a good place to start. So I think for the purpose of this course, Miniconda is also fine. You can just go on installing the packages along the way as and when you realize you need them. So I've been mentioning these things: functions, modules, packages. So these are just very fancy words for things that you'll be using on Python, which I would give you a short preview of. But before that, you should also know how to use Python. How do we write commands? How do we write a script for automating some process? So you can use Python on terminal or command line. So as Chetan mentioned earlier, you have these many commands to navigate between your system. You have these commands to create files, delete things. In the same way, you can use that same platform to even write Python programs, and not just for Python. It is also true for other languages, but here we'll be focusing on Python. So you could use terminal or command line if it's Windows. You could use text editors and scripts, or you could use notebooks. I'm going to show you how each of these work. So in a terminal or command line, it's basically line by line programming, meaning you write this one line of code, you run it, and then you go to the next line. You cannot just write a bunch of code together and run it all together. But the best part of terminal command line is you can see what's happening in real time. You can import things, you can import or install modules. What are modules are basically this sort of library of many subcommands that you would need, and the library usually represents one whole function. So, for example, as an example of line by line programming, you can see this terminal window over here. It's basically, so over here, I've just taken two variables, A and B, and then I add them together, and I print the result, print A plus B is equal to whatever A plus B is. So because A and B was 3 and 5, A plus B is equal to 8. So you see, I've imported something called numpy. Numpy here is a module. It basically has a lot of mathematical operations. So I import it to use functions within numpy. So a function within numpy is linspace, as you can see here. Linspace basically creates arrays of numbers for you. If you define a starting point, stopping point, and how many elements between that starting and stopping points. So you can import modules. You can also install them. So over here, I've tried installing a module called matplotlib. As you might infer, it's basically a plotting library. It has a bunch of functions that let you create plots and modify those plots. But I already have this module with me because I have Anaconda, and also it's a very, very basic module. And that's why I have this requirement already satisfied message, multiple of them actually. And yeah, so that's kind of one way to check if I have the module or not. But if I did not have the module, then you'll see a bunch of messages that shows how the module is being installed. So that's about using terminal or command line. The next way is using text editors. And these are kind of similar in the sense that you again write different lines of code. You can write all the functions that you need, but then you would run it together as a script. So the syntactically speaking, this is the reason I wrote syntax in the title is to emphasize that syntactically it's basically the same as running it on terminal or command line. But instead of line by line programming, it is a script programming, meaning you're just going to write a bunch of lines of code, save it as a script, which is a .py file, and then you can run it. So you have something, you can use basic text editors like TextEdit on Mac or Notepad on Windows, or you could use Sublime, which is a slightly advanced text editor. The advantage being it actually color codes the syntax. So you could see, so like a function would be a different color from an input, and then a number would be a different color from a string input, like that. So you could create, but you could also use Notepad. So right over here, if you see, I created this file called sample_plot.py, where it's just a bunch of code. It's not color coded, it's simple, but it's saved as .py. Then you go to your terminal or command line and you type Python, or if you want to first move to the directory in which your file is saved. So I saved it on my desktop. So I follow CD desktop, and because I start from my main root directory, I go CD desktop, and then I type in Python, the name of the .py file with the extension, and when I run it, I get that plot. So I did plt.plot. So I imported this module with the submodule as plt. I plot it and I show it, and as a result, I get this figure right here. So this is using a text editor. But there are also script editors that are script editors like Visual Studio Code and Spider, which are basically these coding environments. You could write code there, you could write your script there, and within that you can actually run it and you can see your results. So after going through this, I will quickly show you that very shortly. So this is about using text editors and script editors, I guess. So this is what Spider would look like. You basically write your code, and then you can you have the option of running the whole thing, and you can see the results. So I print hello world, which is the very standard basic thing that you do when you first learn programming, and then I do multiplication over here, and I get what the product of these two numbers is. But you can also use it to display a plot, which I'll show you shortly. And if I had a plot, I could see it over here. And then there's this option Variable Explorer that lets me see what variables I have created and what's there in my memory, how much space it's taking in memory, etc. So now Python notebooks. Now, what is a notebook? It is kind of like a regular notebook where you can write things, you can draw things, you could do you could do a bunch of stuff with your notebook, right? So a notebook is a much more flexible, much more interactive version rather than simply writing your code on a text editor. You could write a small portion of code along with rich text. By rich text, I mean, text with formatting and images. The tutorial is written in Jupyter Notebook, so you can see how well formatted it is. Jupyter Notebook is the default Python notebook format. That Jupyter Notebook architecture has also been used for some cloud-based options, Jupyter Lab and Google Colab. Jupyter Lab is also hosted. It was also Anaconda thing. Google Colab, as the name suggests, it's like coding on a Google Drive. Okay, so the Python tutorial was written in a Jupyter Notebook. That demonstrates why, and I will show you quickly, and you will better understand why a notebook environment is preferred to, writing your code on terminal or a script editor, and how it being interactive makes your experience so much easier and so much fun. So a quick introduction on what software and data carpentry is. It is this very, very helpful website, which has a bunch of resources that is put together by volunteer instructors from universities and just independent groups all around the world. They have amazing exercises and tutorials to get you familiar with not just Python, but most programming languages that you need, including like the super new ones that have come up. And so they have exercises, tutorials, and you can also see announcements for various workshops over there, which teach you very specific computing skills. And you can pick and choose based on what your field of research would demand from you. So let's go to the Python tutorial. So this is a tutorial I've designed for you. I've begun it with some, really short answers to all these questions and the things that I discussed in the slides with screenshots of what things look like. So yes, I would first show you how Spider looks. Let's see. Okay, you can see it here. So basically, as I said, you can create Spider is a Python script environment where you can write script and you can run the whole thing without having to go to terminal to run it. You can see the results right there. So you could create plots, you could see your plots, and in the console, you could see the other text output. And whatever error messages you get, because I made a mistake by not importing NumPy first, which I later corrected, you can see my error there. So you can see all your outputs, and it's actually beautifully designed. Visual Studio Code also works the same way. Or because this is a .py file, I can, if I don't want it to be this fancy, I can just go to terminal and run it. So this tutorial, as I mentioned, has been written in a Jupyter Notebook. Well, I'm running Jupyter Lab right now just because I like it a little better. But the architecture is essentially the same. So this is a basic. This is just for you to visualize how Jupyter Notebook, how the whole notebook thing works, and to get you acclimatized to this environment, because this is what you'll be using very shortly. So you can, instead of having to run all lines of code together as a script, a notebook enables you to break your code into these little chunks called cells. So in this script, as you can see, I had to run this first part before running the second part, even though this first part over here that has nothing to do with my plot. My plot, like an entirely different set of data, the things before that's an entirely different thing. But here in the notebook architecture, because we're breaking things up into different cells, I can pick and choose what cells I want to run. I don't need to run the whole thing to get to the last bit. I can run this, and then come back to this. So let's do that. So first I import these libraries that I need, NumPy and matplotlib.pyplot. What are these? Why I have written it, import something as something else? Is basically I'm aliasing it. I don't want to write these big words over and over again, so I just write these just few letters. And referring to NumPy as NP and pyplot as PLT, it's a very standard way of aliasing it. You will learn more about this next week. So Shift and Enter, I can run the cell, and for some reason it's taking a while. Okay, it did. And I can skip this if I want, because like as I said, it's not relevant. So I'm just going to go to the plot. And so as you can see, you have these texts that I've written following a pound sign. These are comments, and it's very, very highly recommended to do so for whatever piece of code you write. Because when you're writing code, you could imagine you're writing something for someone else to see, not just you. So you don't want to forget, you don't want to be the only person who can read your code. You want to be able to share and distribute code eventually, because that's how open software works. That's how writing pipelines work. So you would essentially want to write comments. You could write one-line comments by putting a pound sign and then writing whatever you want, or you could enclose comments in triple quotes like this. So this is to create a very basic plot, and there you go. Now, this is something very basic. I can also read in data from an external file and plot that. So in astronomy, especially for those interested in observing, whenever you observe, you observe something on the sky and you save the data from your telescope, and then there's like a bunch of processing it should go through. The final result, even the observed data, is saved as something called a .fits file. .fits is extension. So to whatever operation you need to do with that, you need to have the separate astronomy package. So astropy.io is a very, very important astronomy package. And from that, I import this module called fits. And now I can read my data using fits.getData from this image that I've saved in this directory. The writing what my directory name is, it follows the same Unix way of defining your directory, your subdirectory. So I'm going to run this cell. Oh, sorry. But now you see I get this error because I forgot to import my module. So now I run these, and now I can. So you don't need to exactly understand. I understand this might be a little overwhelming, but all you need to know is that this image is basically a giant matrix. It is a 201 by 201 matrix of data points. So which is like what, over 40,000 data points, each having a certain value. What the value of the data point is, it will typically be given by this thing over here. And I can technically adjust what my contrast limits are, so I can actually see what my data point is. Okay, this is curious. I don't know why it's doing this. It certainly did not do this before.
I can see the data. It's just sparse.
Okay, yeah. So I think it's probably just me seeing it then. All right, but yeah, you can adjust contrast limits. There's a bunch of stuff you can do. You can adjust contrast limits. You can adjust how much of the data you want to see. Right now, it's just restricted to a small portion, but you could define your axis limits. You could change your axis labels. You could change the image size. You could even change the color scheme. There's a lot of different things you can do to visualize the data as much as you want, as you prefer. So this is 201 by 201 is not that large of a data set. Now I'm going to show you how Python is actually much more powerful than this. So I'm going to read in a file that contains 20,000 rows of data distributed between 97 different columns. So that's 20,000 by 97. So that's like what? 2 times, yeah, that's like a lot. 2 times 10 to the 6 data points, 2 million data points. There you go. So I'm gonna read in all of that and then use 2 columns to create a scatter plot. And this you might have actually seen in the 2021 version of the tutorial if you've explored it. So this is another very, very useful library module called Pandas, which is used to import and read in different files. So there's a .csv file which gives you the 20,000 closest stars from the Gaia archive, the DR2 version. The DR3 version has just come out. And so you can see how quickly that was plotted. There's like a huge bunch of data points that I plotted just like that. It might be a tiny bit faster. My computer is definitely slow. So again, you can change how you want to visualize this. You can change the size of your scatter points. You can change the colors. You could read in more data. And this is just 2 columns. I could also read in 3 columns and make this 3D plot, which you're free to explore at your own time. So the whole point of this exercise was just to show how versatile Python is, how much data it can read in so little time, and why it is a very, very handy tool to use, and why every astronomer should know how to use Python. And as I mentioned earlier, here's a link to the software and data carpentry for Python, which would give you a good idea and has a bunch of exercises to get you familiarized with the language and the environment in which you'll be working with the language. So that's not all I have, and this is your assignment. I would advise you to go through this tutorial and repeat all of it on Google Colab, so it's a different environment from what I used. Make sure you understand it, and you can feel free to add your own comments along the way to explain to yourself what you've been doing.